Good. Thank you. Thank you so much. Yes, it's my pleasure to be here today. Otherwise, it would just be another working day if you were not here. And it's a pleasure to see my colleagues for our new Nordic network. I look very much to our ongoing and beautiful collaboration. My talk today, the Energy Metaverse, catalyzing the green energy transition in smart cities, is also related to a similar talk I'm going to give next week in South Korea for the Smart City Expo. So that actually inspired why I'm going to use the smart cities as a case for discussing what we do with our research on the energy metaverse. But there's also another reason why I like to use the example of smart cities, as you will see, because these smart cities are quite different from what we are used to when we live in the Nordic. And therefore, it's quite important also to understand what does the world outside the Nordic look like. Because as Klaus just mentioned in his talk, one of the things that are important for many of the funding program is also to create growth, jobs, and very often this job creation and growth happens through export. So we actually also need to know the world outside the Nordic if we want to think about the kind of solutions we can create and we can export. So I will basically start from the back. I mean, of the end of the title, and start talking about smart cities first. Then I will talk about the next part of the title, the green energy transition, and then come to the front of the title, actually, what is the energy metaverse and what is the research we are doing in order to try to understand the needs and understand how to create green solutions that can help in contexts like smart cities. So let's start with some of the challenges that we see globally nowadays in many of the world's cities. The first picture you see up here is actually from New York. You probably recognize all the yellow caps. You see them in all movies around New York. There are plenty of them. They are old, they are dirty, they are polluting. They are really not nice to sit in. So take an Uber when you are, because that would be a nice new car with a safety belt. But actually, it's a big problem. There are congestion, it's slow traffic, and it's pollution in the air. So it's really not good for health. So that's also one of the focuses of smart cities. It's actually how can you improve the living condition, the environment, and so that you get more sustainable, livable cities. Another thing that is a big issue in many places is actually the waste. The waste that are being generated when you have millions of people living in a small geographical area. Small geographical area can be relative because if you take a large urban area like Beijing, it's the same size as Zealand. So then I will not call it a small geographical area. It's not, at least not in a Danish context. But actually the pollution from waste that are simply just left in nature, this picture is from Panama City, is tremendous. And of course, there are a lot of issues that are also related to water management. Actually, how are you sure you get enough water? It's also a global problem when it comes to cities. If we take a city like Jakarta, the capital of Indonesia, it's sinking 25 centimeters each year due to the pumping of groundwater. And when you sink 25 centimeters each year, and at the same time you have sea level rises, then you can figure out what happens in a coastal city. It gets a lot of floodings. So that's also a challenge for cities globally. And then it comes down to things like aging infrastructure. That is not only like the roads you saw, it's also the whole energy infrastructure. The wiring of the distribution grids in cities are really outdated. And the same thing when it comes to heating systems. And that can very often lead to power outage. This is at the Lower Manhattan when they had this storm coming in. I think it was Sandy that actually flooded Lower Manhattan. and most of the electricity was lost because simply the transformer station was flooded, and then of course they had a short, and then it turns out the only buildings that keeps the light on, as you can see here, is actually the building that was connected to the gas grid, because they have their own power generator in the basement running on gas. So they actually have their own little microgrid or in the building that allows them to actually have the lights on. So these are some of the global challenges we see that have triggered this whole mega trend of building smart cities globally. One of the first smart cities I had the pleasure to visit was back in 2014. It was Rio de Janeiro. They have been an early mover on the whole smart city concept. So that was part of smart grid applied in Brasilia, the capital of Brazil, and then the foreign minister was also so nice to invite me and also take me on a tour trip to visit the Smart City Control Center in Rio de Janeiro. And the interesting thing here is that it was actually a mayor decision to make Rio de Janeiro into a smart city due to an event they had in around 2012, where they had a lot of rain and they had a lot of mudslides. So they actually had a lot of people who was injured and a lot of people who died and a lot of people who could not be rescued because, the rescue workers could not find where they were. So it was a disaster. So based on that, he took the decision that Rio de Janeiro, they needed to have a smart city control center that would be able to monitor all the traffics in the city, would be able to monitor where do you have all your rescue workers, where do you have all your police, and where do you have all your critical infrastructure or critical public institutions. So they built this within 2 years. They built a new building. They equipped it fully with connected IoT equipment into the whole city such that they could actually monitor all the traffic. They could monitor the location of each police officer and each rescue worker, and the same thing for medical care. And they could monitor all traffic congestions and what happens if you close a road, and they could see with forecasting how that traffic congestion would propagate to other roads. So that was really amazing. It's simply built on top of Google Maps. With the makeup on top of Google Maps, they can put in all these different layers where then they can see, critical infrastructure, and they can see the location of the employees. So it's a quite interesting case. Similar in New York, through collaboration with the Danish Clean Tech Hub in New York City, had the opportunity to actually learn something about the smart city projects that are ongoing. This is a little bit different. They don't have a kind of a central control center in the same way as we saw in Rio de Janeiro, but they have started a lot of innovation projects to try out technologies in the city to see, how it could be adopted for larger scale up. So basically, they run through and some of their innovation incubators, small funding programs where companies can go in and they can put a bid on a tender. Basically, these innovation challenges comes out in kind of a public, similar to a kind of a public tender, and then companies and universities, they can make a bid, say, okay, we will take this challenge and we will in the city implement solutions. And they have been running that through a number of years. And it's quite successful way of doing it. So it's quite interesting to see how this becomes smart city solutions that are actually in use. They have done a lot on monitoring of trash bins on Lower Manhattan in order to optimize, how you should empty them and clean up the city in that way. They have done a lot on smart grid programs and introducing renewables into the city in different areas as smart grids. Does this come up here? Good. Yes, and my last example I have is from Shanghai. Shanghai have invested a lot, both in city scale control center where they can monitor everything within the city. But they have also done something else, and they're one of the first cities I know of who have done it. They have started to make a digital twin of the whole city. Shanghai is big. I mean, it's huge. So they have simply made 3D models of the whole city that they have integrated with the whole traffic management and with monitoring of the energy grid, then to see actually how energy is being used in the city. Of course, doing something like this also requires quite a high or large budget. So, I mean, funding-wise, I think this is state money that have been funding it. But it's quite interesting to see also in a case like this, actually how it also have been used to provide various kind of public services, especially within transportation, optimization and transportation and autonomous buses that will bring people around. So if we look at these cases and many of the other cases that you can find online for smart cities, you will actually see that they have something in common, or what they have in common is that they very often have a focusing on how can you optimize the use of resources. I mean, any kind of resources, water and human resources and energy resources and all these things, how can you optimize it? And at the same time also use information. You both use data and information to see how you can optimize, but you also use data and information to see how you can make sure that you have a much higher utilization of your resources and thereby also have a much higher efficiency. And all of that together also helps you to reduce pollution. And the sectors that I've typically focused on is things like smart public safety, to make sure that the city becomes more safe, especially when you have so many people in the same place. And also, how do you make your transportation more smart, so you can better monitor both, your car traffic in the city, but also when it comes to trains and keep that operational. And then, of course, when it comes down to things like waste, water, how do you make buildings more energy efficient? That is what we call smart buildings here. Smart energy is that when you start to see how can you do kind of demand response between the buildings you have in your city, the transportation systems you have in your city, and how it relates to the energy system. And then what we have here, like the smart city operations, is basically referring to all the smart control centers. Good. So when we look at what makes this possible, actually what makes this possible is some of the things that we actually have heard about for many years. So now Internet of Things is an old news, but the thing is that now it's actually deployed. It's actively collecting data in city environments. And the data that are being collected is basically big data that is then being used for doing a lot of analysis. But it's happening. It's not something that people are just talking about. We actually see it being deployed for practical applications. And these practical applications is, of course, also where you see a lot of SMEs have been created globally because they deliver solutions in the context where there's a problem. I mean, local problems, local solutions. But still, if you want to develop a solution and you would like to export it, you also need to know what does these markets look like where they have problems. And of course, many of these things are running either on edge computing, where the computation is close to where it's needed, or it's all data that are collected and goes up in the cloud, where it can be used for more application based on artificial intelligence. And that's typically a lot based on forecasting. Forecasting of will there be traffic congestion, forecasting of what will be the demand side for the coming period, of load cost of production forecasting for what will be the energy production. So this is basically the whole infrastructure we are looking into when we talk smart cities. Now I would like to talk a little bit about the thing with the green transition, because the need we have seen for a green transition in relation to our cities is that most large cities, large urban areas, or what we also have these smart cities, they are subject to basically overheating. Because when you have these dense urban areas, you typically have a lot of concrete, you have a lot of asphalt, you unfortunately have very few trees, green areas. So you typically have what is called this urban heat island. So it becomes very heated in the cities. And this has become worse due to the climate change we see, because as you can see on the globe, there are certain areas where we also have very high population of people that are becoming much hotter. You cannot see US on this one, but if you take a similar for of North America, you will see that for the whole East Coast, you see a similar dark red area. So that probably tense area will also see similar challenges. And you can see for India, basically where most of India population is living, is going to be very warm. And the same thing if you go over in Asia and you see where most people in China live, it's also going to be much warmer in the future. So climate challenges is a big issue, both to heating, but also to the extreme weather events we see with flooding in cities. This is a picture from the flood this year in China. So what all of this leads to, when we look at it from an energy point of view, is that we will see that we will get an increase, immense increase in the cooling demand. So we are going to need much more energy for cooling. And if we do it with the good old-fashioned aircon way, and just buy more aircons, of course, our electricity grid is going to be really overloaded. So we need to have more kind of smart solutions here, or a way of controlling it. So that is really going up. I had some numbers here when you just look in a country like US, who have built out with air conditioning in many years. I mean, since the 60s, you also see that you have some numbers that that will increase even more compared to what we have today. And there's maybe that's not so much. But this just shows that countries that already have a lot of air conditioning, and even some of them might have some smart thermostats, but they will increase. But the real challenge is not really with the countries in the top here, like Japan, US, and South Korea, where a lot of the households and offices, buildings already have air conditioning. Yes, they will use more. They might also have money to do it smart. But the real challenge is actually when you look at the bottom of the list, and you remember the globe from before with the red areas. So what's going to be a real challenge from an energy point of view is that in countries like India, Indonesia, and Brazil and Mexico, they also start to want to build out with air conditioning and the energy demand that follows from it, and the list is much longer. So globally, there will be an enormous need for energy when it comes to provide air conditioning. And air conditioning is not provided in a smart way. In most cases, air conditioning is typically provided with these individual house units that are not really so energy efficient because they have to be cheap. So you don't see a good cost factor on these ones, and you just put them off. So there's some places where they do it more smart. One case is, for instance, in Hong Kong, where they have just, they are in the process of finalizing the transformation of the old airport that was inside Hong Kong. That is actually being transformed into a new mixed-use part of the city with commercial space, shopping centers, and offices and residential apartments. But there they have built a large district cooling grid. So all these new buildings that are being built are provided with district cooling. And they're also working on 9 to 10 other district cooling systems inside Hong Kong. So they are moving in the new part, they're moving away from something like you see in this picture, but still, if you go to the old part of the city, you will see this kind. So that is indeed, I mean, an energy challenge and also a kind of control challenge. The other thing we see at the moment, at least we talk a lot about it in Denmark and Scandinavia, and Norway is a little bit ahead of the rest of us in adopting of electrical vehicles. So it's a big trend that we all have to drive an electrical vehicle, because then we can reduce CO2 emission in cities, and we can utilize renewable energy in a better way. But one of the things you will see if you travel around, here's a picture just taken a few weeks ago from Panama City, and you will see that actually the distribution grids are really bad. I mean, and I would like to show this picture because when you walk around in Jørgensen and you say, where is the distribution grid? I mean, there's no cables. Where is it? It's because it's below you, right? So we took our whole distribution grid and we put it in the ground. So we don't have any ugly pictures like this because it's below you. And if we have a storm, we don't need to care because our grid is resilient in that way, at least the distribution grid. But if you have this kind of distribution grid and you want to start to charge a lot of electrical vehicle inside your city, it's not going to happen because your grid is simply not strong enough. So either you need to do a lot on smart charging in some way, or you need to do a lot of grid reinforcement in order to solve this. And the problem is, I have something that comes up all the time here. I don't know what's wrong with the PowerPoint. Okay, but the problem is actually that we have a global goal of having many more electrical vehicles in the world. And we are actually having more electrical vehicles. But the issue is that if you look at the global number of cars in the world today, we have 4.5 billion cars, also cars, and they're not going to go away tomorrow. And many people will not be able to afford just buying an electrical vehicle. But there are a growth in the adoption. We have some numbers here where we say actually the large adopter at the moment of battery driven electrical vehicles and hybrids is actually China, who is leading. Then we have Europe coming in, and then the United States, and then the rest of the world. So it takes a time, I think, before we see really electrical vehicles everywhere, and before we see the 1.5 billion of cars displaced. So, but it's one of the city challenges or grid challenges we see everywhere is basically cooling. We need to have much more cooling in the future, and it's also charging of electrical vehicles. Now, there's just one thing I always like to remind people about, because I noticed that Klaus in his slide, he had this, that we need to have sustainable, social sustainable solutions. So I like to put this slide up when we talk about electrical vehicles, because the battery that is inside our current electrical vehicles are definitely not social sustainable or environmental sustainable because of the because of the cobalt, and because of the nickel. So if you look at the pictures over here, this was a rainforest in Indonesia, and Indonesia is becoming the world's largest producer of nickel by simply just cutting down all the rainforest and making it into nickel mines. So the coral reef is being destroyed by soil that floods out in the water and so on and so forth. You see in Chile, in some of the desert region where they produce a lot of the lithium, they use whatever water is left to wash out the lithium, so all the local communities have no platform for life. And if you go to Congo, that is the world's largest producer of cobalt. No, it's not blood diamond anymore, not blood cobalt. It's actually happening under terrible conditions where people have mined it with their bare hands next to some of the huge international companies. So this is just a point that we need to remember each time we sit in an electrical vehicle with an lithium battery, that we are not so green and so sustainable as we believe. But there's hope, there's solution coming up when it comes to batteries because they are the sodium ion. That's just the salt you use on your food every day. Good. So when we go into the adoption challenges, actually for actually production, when we look into it, we see that there's a huge adaptation of photovoltaics. But the thing again, just like our grid is not built for charging of EVs, our grid is not built for actually have a lot of production locally in the grid. So that's also a challenge for the distribution grid. But again, there are kind of solutions for that if you have co-consumption with co-production. So if you produce the electricity while you need it for cooling, then of course you will not put any strain on the distribution grid. But of course, all of these things again needs to be coordinated, both being forecast and being controlled. So that's where there is a large need for systems. Good. So now I'll get to the point about the innovation and the adaptation of these smart city solutions and look at them in a global scale. And that's why I like this picture, because this picture actually shows us the world. I mean, it's the world by night, but if you look at the night, you also see where do we have actually our electricity consumption and where do we need the electricity, the renewable energy. So if we look at the challenges that these regions are facing, because remember, I mean, the globe from before with the red areas, it's somehow, it's actually around here that is going to be very red, will have a very high cooling need. It's also the place that are going to have a lot of electrification for transportation. And it's also the places where we will then have to reduce our CO2 emissions by having large integration of renewables. But these locations also have very different regulatory frameworks. It's also very different economical capabilities and different political goals. So where we in Europe talk a lot about reducing CO2 emission in order to have better climate, and what we learned, for instance, for the collaboration we have in Indonesia, there's a lot of focusing on actually improving economical growth by making more energy cheap available. That means actually use more of the natural resources and food. So there are huge differences globally when it comes to these conditions. So how do we then start to think about how do we make decisions about this when we're going to develop these solutions? I mean, we have to deal with all these differences in the conditions, and we are still trying to make some solutions that are globally applicable. If we want to create growth and we want to, growth in Europe or growth in Scandinavia, Denmark, and create jobs, but they also need to be able to be exported. So I tried somehow to capture some of the things. I mean, if we look into the system we have here, our energy system of the past, I mean, we have a lot of past decisions that is based on different reasons, like the culture, the economy, the politics, the technology, and the climate. Let's give all this past. One of the things we fight a lot with of these past decisions is that in Denmark, we have our distribution grid that is designed for, no, it's not designed, but it's sold. I mean, 25 amps for each endpoint, each customer, but basically the grid can only deliver 5 for simultaneous use. So it has under capacity. So that's one of the challenges we have. And that's basically something that determines where we are today based on past decisions. So now when we are going to think about how do we develop smart solutions that can help us solve these problems when we look into the future, well, then the decisions we are actually going to take is going to determine what branch we will be on in the tree. Because if we first have made those decisions like we did in the past, that put us here, understand? But when we are going to make new decisions, we will end up in a certain direction and we will not so easily be able to shift from one direction to another. So that's the complexity we have when we need to, develop our energy system further. And we think about how digitalization can help us in that process. So this is one of the challenges we have tried to address by creating what we call the energy metaverse. And I'll just start, in order to frame what we mean with the energy metaverse, I would just like to, put up this these pictures of the metaverse as we know it. So you all have seen Meta's platform back in 2021, where he somehow tried to reintroduce, Mark Zuckerberg tried to reintroduce the metaverse. And you also, many of you might also have seen the Matrix, right? But what you probably don't know is that SDU was an early mover on the metaverse. We actually had our campus online in 2003 in Second Life. Yes, come on, we were early movers. And we actually talked about doing classes in Second Life. But okay, we never happened, but we were there. So the point is just that, the whole idea of the metaverse was not really a new thing, even though it was reintroduced. And for some people, it might have been new in 21, but it's quite old. So, but it's basically, creating these virtual worlds that people can project themselves into and exist in. Now, what we have been doing is that that we create the energy metaverse. And in the energy metaverse, what we do is that we try to make this virtual replica of the whole energy ecosystem, not only the energy system, I mean the physical part, but also try to get all the regulations and cultural different things and everything into the simulations we are going to do in the metaverse, such that we can explore what happens if we make changes. So it's basically, we are taking physical parts, put them in the metaverse where they can interact with each other, and they can also interact with, physical parts from the outside can interact with virtual parts in the inside. So that's where we are now, where we can do software in the loop. That means that we actually have software that are running outside the metaverse that can interact with physical, virtual things inside the metaverse. So in the normal metaverse where you have a person who projects themselves and interact with things, we can have softwares outside that interacts with things inside the metaverse. But you will see more details what it looks like. So this is what we try to do. Remember the tree from before, right? The roots of the tree that have determined all the decision. This is actually also what actually relates to the layers that we have in the energy ecosystem. Energy ecosystem exists somewhere in the world. It have a geolocation, just like when you remember the picture of the Earth by night, and you have all the lights. That's basically different conditions in geolocations. Then due to what happened in a historical timeline, you have different types of and qualities of the energy infrastructure that adds actually up to the society level. This is your smart city level, where you have your buildings, your roads, or public services, and so on, and the decision makers, and actually all the citizens. So this is the universe that we try to model aspects of in the energy metaverse by using digital twins. How am I doing on time? Take my time. Okay. Good. So these are actually our dimensions for analysis. We have developed a methodology to try to analyze these, we say, the 5 C-step dimensions with the climate, social culture, technological readiness, economy, and policies or relations. Because when you want to create a metaverse that have to represent a real world, you really need to understand the whole setup, because if you really don't capture the essence of that location with that infrastructure, with those people and with those regulations, then you cannot really do these what-if scenarios. But you cannot just create a new simulation each time
you want to explore a different place. So you also need to find ways of trying to capture commonalities, such that you know what are the differences when you go local. And that's what we try to do in this methodology, is that we systematically can cover these aspects such that we can create more reusable energy metaverses that can be easier adapted to different locations. But there's a few papers on this that is accessible on our website if somebody wants to know more. Yes, and who is then going to use it? That's one thing we always ask when we do something at the university. Yeah, you have a lot of fun. Who is going to use this? Is it useful? Can it help anyone? And we do believe it can be very useful. And those people we see as users is, for instance, I mean, our local, also National Ministry of Energy, because they need to make some wise decision about the futures. And today they really don't have so many tools to do it. Because they really don't know what the consequences of the regulation they make. And nobody are really interested in making solutions that try to explore those regulations because they don't know if the customer dares to adopt it. So that's why we see that if we can try out the consequence of regulations in a given energy ecosystem before they are actually introduced, then you can somehow evaluate if it's a good regulation. You can also try to change. I mean, this is the energy ecosystem as it looks today, but you can also try to configure it as what it should look like in the future, and then see how the regulation works. And then you can start to work with the transition from the current state to the future state and see what happens on that roadmap. So that's why we think, when you come to national ministries of energy, it will be very useful. And also the energy agencies. I can see there's one thing I didn't put in here. Funding agencies. Yes. Because this might also help, what would be a good grant solution or, grant challenge or similar. What should we explore? What is the scope in which we want to explore something? But basically, it just gives us all the way down, local authorities, that can be city governments. If they want to make changes in the city, they can try it out before they actually they do it. It can be our system operators like ESOs, TSOs, who can go in and see what is the consequence if I upgrade my transformer, or should I just put a battery in the grid, or should I have household batteries, or should I tell people living in that area that, well, sorry, pal, you have to take the bus because we cannot help you charge your EV because capacity is gone. So there are many scenarios that can be explored. Good. So that is basically our use cases. So what does it look like? Well, what we do is that we take the layers from before, modeling the dimensions, and write the software to put it into our simulation server. And then, of course, we visualize it in our little city control room, energy meter lab control room. Now, I didn't manage to actually buy this one online. So we did something different. Upstairs, we 2 weeks ago, I think, we spent a few days on building the physical part of our energy metaverse lab, where we can visualize actually all the outputs that comes out of our simulations. Some of you had the pleasure of seeing it demoed for the first time yesterday. And what we show here is some of the work that we have been doing on building the digital twins of our living labs we have here on campus. That is actually buildings that we can use inside for simulating what happens on the demand side. So the work we have here will continue focusing on what happens if I step on the so what happens if we improve the smartness of the building control in order to make them more grid integratable. So we have a few new annexes coming up in relation to the International Energy Agency that is focusing on more grid-enabled buildings. So what we would be able to do in our platform here is that we can, with software in the loop, we can try software for smart building control on the model of the building we have, and then see how the indoor climate will be in the building when it responds to demand response signals from the grid, and then see how much flexibility can we provide without having discomfort for the people using the building. So that's what's ongoing there. Other work we have done in recent years, some of it we have finished, some of it we are continuing, but this is actually work we have been doing in a national project called Flexible Energy Denmark. You might hear more about it later from another speaker this afternoon. But what we actually did here is that we took distribution grid from one of the partners in the project, Nørregaard, and then we made a digital twin model of it such that we could explore what happens due to the adoption of the EVs in the grid, and what happens if you start to either have electrical heating or if you use heat pumps or radiators in the building or in the grid. So and then basically we could try out different smart charging strategies and compare them with just simple charging, where you basically just charge whenever you come home and you plug in. That work have now been extended such that we have a new version of this system running, where a third-party software supplier of charging software can actually run his software in a server. Just like he would run it if he wanted to interact with real customer cars. But the software will now connect to this energy metaverse, and we will be able to charge virtual charging boxes on virtual cars. So, we will not cause any grid overload in the real world. We can do everything safely in there. So it becomes kind of a sandbox for trying things out. And the other thing that becomes interesting is that we can try the charging control from multiple charging suppliers. So if you have Clever or whatever you have, and all of them say they have this really, really smart charging, and you try it all the charging suppliers in the same distribution grid, then you can see at the end of the day how many overloads you get. And then I think you will have whatever DSOs like that, because they have no way of controlling it. So this is what we explored. I always love to talk about these results that was created by some of my younger colleagues, because it somehow showed what we already knew, but what most people probably don't know or will not accept. Because it actually turns out that if you just charge your car whenever you come home and plug it in, you don't get so many overloads when we have this full adaptation adoption of EVs. But if we do what we hear so often, people talk about, or at least our politicians say, we need to use electricity when it's cheap. So we're all going to charge our electrical car when it's cheap. Right? That's not rocket science. That's not going to work. Yes. So because we actually see that if all of us charge when it's cheap, then of course we get this flocking behavior or behavior, and it spikes at the same time. It's not a good idea, but that's actually what the software is doing in its current form. And then of course there was introduced something that was called the tariff model 3.0 that should help, just that we this should help us to use even more electricity when there was not so much grid load, and that also means use more electricity. I mean, when the electricity is cheap, basically moving our consumption to nighttime, and that just makes the situation even worse with grid overload. So this is one of the things why I think the platform is very useful to do these kind of what-if scenarios, because what you can also do here is that you can explore other charging strategies. You can explore other tariff models for moving consumption, and you can explore other pricing schemes, real-time pricing or other form of electricity markets for day-ahead markets. And then you can see what will be the consequence down in the distribution grid. Yes. So I think that was my introduction to what we are doing in this space. And if there's any questions.
I think maybe you are going to have open up the first question. Is it possible during the lunch break you open up the Metaverse lab and have people can go to have a look at beside the slide?
Here it's possible. Yes.
Yes. Yes.
Yeah.
Then we'll have any questions?
Yeah. I have one. Thanks for a very nice presentation. You had this very long list with potential users who could have benefit from the energy metaverse.
Yeah.
So how can the potential users and maybe also others contribute to it? Because I think many people already have single models, data, knowledge, competences, test systems and stuff like this. So how do we put everything together in kind of common frameworks?
Yeah. I mean, one of the things that we support when it comes to the modeling part is like FM use, I mean, such that if you have done some modeling, it can be hooked in. Because if you come with, your own model of your battery, or you have made a heat storage, I mean, in some way, and you already have been doing the calculation of it in isolation, and now you want to see how it operates in a system perspective. Like then is why we try to support that we can easily integrate these parts. Because that's of course a key point is that for any of things of this to be economically feasible in the scope we live in, it also means to be very flexible and adaptable. Yeah. And of course, what we hope to do much more in the coming years is, of course, to run more what-if scenarios with stakeholders. And now it has been possible for us to do something with the distribution system operator through the Flexible Energy Denmark project. And we have done a little bit more in the Digital Energy Hub project that is coming to an end now. It was funded by the Industrial Foundation. But we are working on, of course, continuing that line of research. Yeah. And then for integrating the software in order to easily facilitate software in the loop, what we do is that we use the real-life protocol. So for the charging scenarios we have here, we use the Open Charging Point Protocol. Mm-hmm. And so that should make it very simple for a software company who's making these solutions actually to hook into the virtual world. Yeah. Yes.
It sounds like a really great platform, and I think it's something that we really need, especially in terms of exploring these what-if situations. And perhaps my question is slightly out of scope, but I find that sort of working in the industry, and just to give you an example, I work in cooling and optimizing cooling systems where we just put an IoT solution on top of some sort of energy system. And we say that, by using our solution, you can, reduce your CO2 emissions by something tons, right? And when we say that, they go, okay, great, what now, right? Yeah. But when we say something like, oh, you can save something, 1,000 Danish crowns, they go, oh, actually, that's great, right? Rather than the previous thing I said. So my point is that there is sort of a huge gap in between, of course, running these models and simulations and also communicating that data. And it makes sense now that we communicate in these very fancy statistics and graphs because we're in a very academic setting or really sometimes industrial, but to the someone who is a building manager or to someone who's just operating systems so that their customers can have cooling, it doesn't really matter to them if they save CO2. It matters to them if their customers are comfortable, if they can save the energy bill.
I mean, with the new EU regulations, actually, you need to meet certain climate goals, and you need to document that you meet them. So that's this whole IoT part that you need the data, but you need to document it, and that's a regulatory requirement. So in that way, they just have to implement it. End of story. But I think for your question, when you ask, what is the benefit of a solution? I mean, most times you can only refer to what was your experience, by previous customers that look similar, right? But what we try to create when we create these energy metaverse is that we, through simulation of the case, can show what is the potential. Of course, there's always an uncertainty. But in order to, learn more about this uncertainty, we work with our own buildings here. I mean, we work with this building, and we work with OU44 over here as buildings where we have the real data. We know everything about how they are constructed. So we are actually able to, make simulation of those and simulate changes to them and what will be the impact, such that we at least know how methodology is working. And then, of course, what I think can convince or be more convincible to people when you can show cases, real life cases where you have the real life thing and you have the simulation part, or in terms of the digital twin, and you can actually show that, these things shows you or behave as you expect them to behave when you run them over time. And I hope that's something that can help influence people to adopt more smart solution, but at the same time also help us to make them such that what we do actually works, right? Because if we fail a number of times, I don't think anybody will, buy anything from you or anybody else, right? Yes.
One question? Hey, first.
Hi, can you talk a little bit more about the storage needs of the metaverse and how to execute that sustainably? And then if the solution is nuclear, how favorable are the regulatory conditions in the countries that could benefit most from smart city adoption?
You mean what would kind of be the computational needs? Well, I think that really depends on what we do at the moment is not so energy intensive. Where we might be moving might become more energy intensive. But I think the biggest issue right now with respect to, energy consumption from smart solution really depends on how much AI you build into them in terms of large language models, because that's where really the huge energy use is. Because the other technologies I mentioned on my slide where I talked about IoT sensors, since they are basically most of them battery driven, they have been developed over quite some years, 10, 20 years. The technology or the whole technology stack is very energy efficient. The same thing when you look at edge solution and cloud solutions, there have been a lot of focus on energy at these, when we look at these big urban centers, right? They are so dense. I mean, if you look at the number of people who live per square kilometer, very, very dense. So the problems they have, of course, also reflects that urban density, both with energy use and with pollution. But if we look at the energy use, I mean, many of the places I have visited in urban dense areas, you know, most of them put a little PV on the top. But when you are like 48 floors up and you put a little PV on the top, that really doesn't matter for what the whole building is consuming. So if you want to project that into a more Nordic region where we are less dense populated, we are more horizontal. So I think we should take this idea, this smart city idea, and then we should transform it maybe into we'll call it smart regions or smart countries. And then say, okay, you know, we have similar challenges, but we are more geographically distributed. And in many cases, we have more space. But we can still benefit from the same kind of mindset in you know, how do we better utilize electricity locally compared to have to transport it and put, I mean, which would require more build out of distribution and transmission grid. Regulatory, we are not so far in Denmark on that one. Other European countries are more moving on the whole idea of energy communities. We are not really moving on it. There was an attempt at Amager to try to see if they could make a small energy community where neighbors could sell electricity to each other, but that was, I think it was killed by the finance industry due to taxation. So I think we could do it, but I think we have some regulatory barriers in Denmark for doing more smart things.
We have one online question.
Yeah, maybe I think you should read it, maybe read it out loud, so you have an idea. The question is quite long, from George from Sweden again.
Thank you for your interesting presentation. How the digital twin actually is designed for compensating discrepancies between the model and the physical behavior of the system. In the industrial robotic field, the digital twin is basically used for testing, verifying the purpose of your robot behavior. Yes. I mean, what we do is, if I take the building here as an example, is that in our digital twin design, we have the state of the building from the sensors we have installed in the building, from the electricity and heating metering we have in the building. So at any point in time, we have the state of the building, and then based on that state, and then based on, for instance, weather forecast and data about previous energy consumption, we would be able to, you know, predict the future indoor climate and predict the future energy consumption of the building. So that means that we basically have a feedback loop in which we compensate for any differences that might be in the model. Yes.